Welcome everybody, Sheldon here with Data Systems Architecture, and this is video 3 in our series, Advanced Concepts in Data Architecture. And we are going to be honing in on something a bit more technical related to scalability and resiliency within our data systems. So when we are designing data pipelines, moving data from one place to another, there is a central pattern that is popular called decoupling our data pipelines. And this essentially ensures that we are able to have resiliency and optimization monitoring while data is in flight between our data sources and our data sinks. So there are a lot of problems that we run into in production while running data pipelines. Data in flight is difficult to track. It is often not replicated. It is often, therefore there's risk of data loss while data is in flight. And if there's data loss, then there's a risk that we don't know about it, and our data sources and our data sinks become desynchronized. And of course, this is defeats the whole purpose of the pipelines. It means you didn't do your job. And so the most common scenarios where we run into these kinds of data loss issues are during insert retry operations, when there are crashes in ingress code, when there are deployments on data ingress code, or when we are making some heavy changes to our data structure itself, such as adding replicas, removing replicas, changing schemas, all of this kind of stuff. And additionally, the overall throughput of our system is contingent upon horizontal scalability. So we may not be able to copy quickly enough from our data source to our data sink through a single container, through a single instance of our application. We may need to run many instances of our ingress code in order to move the data fast enough. And using a decoupled data pipeline facilitates horizontal scalability of our pipeline. The way that we implement a decoupled data pipeline is through distributed messaging systems. But let's check our diagram to see what the three different phases of three levels of sophistication for a data pipeline. Starting with a very simple, most basic way to implement our ingress code, we have a data source, possibly an external database that we need to copy that data and get it into our own database, a data sink. And so we write a script or maybe a custom app that runs continuously, and it maintains an internal state to keep track of which data it has written from the data source into the data sink, so that every time it iterates or every time the script is initialized, it can it can find the records that it needs and continue moving forward in the right direction. And as you can see, the problem with this is that the internal state can be lost if there is a crash. And then if this state is being used to keep track of which records have been written or which records are being processed between the data source and the data sink, then this does not scale horizontally, because the different instances of the application will not have awareness of which records are in flight and therefore will not be able to work. So it is possible to move to a system where we maintain an external state, and this is a bit more sophisticated. A very common pattern is to use an in-memory caching database like Redis to manage and to maintain an external copy of the state to keep track of which data is in flight, so that if our app crashes, then it can go back to Redis and it can fetch that state and figure out where it's got to pick up. Or if there are multiple copies of the application running, then that state can be modified or locked, or you can manage the external state with custom code. But that can become very complex trying to maintain the external state between multiple instances of the applications, or even multiple threads within one application. And so a decoupled data pipeline uses a distributed messaging system to allow us to perform these operations in a way that is facilitates long-term resiliency, higher throughput, and flexibility with our data models, and overall creates an improvement to our operational integrity across our entire data system. And so these data messaging systems, or these distributed messaging systems, most popular being Kafka, RabbitMQ, my personal favorite being Apache Pulsar. There are many of them out there. And we do have a video series specifically on advanced concepts for distributed messaging systems, as well as a playlist discussing advanced concepts in Apache Pulsar as well. But for now, we're thinking very high level, and we're using this distributed messaging system so that while data is in flight, we are creating a replica of that data. And we are no longer relying on the internal state of our application to keep track of which records are in flight, because it is already recorded in the messaging system on the topic, or with offsets, or with ACKs and NACKs. We won't get into the details, but the state management is handled by the distributed messaging system. And this also has additional performance benefits, which we'll talk about after we get into the mechanics, how this works with the diagram. So let's look at a basic example of a distributed messaging system. We have our same data source, and we've written sort of half of our code that we had before and split it into a separate application called a producer. And this takes records from the data source, publishes the data to our distributed messaging system in a raw format, or maybe slightly modified if you want to. And then the distributed messaging system places this data on a topic or a queue, depending, the terminology depends on exactly which system you're using. But in our case, we'll discuss topics. So we now have a copy of our data on topic 1, and we need to get that data off of the topic into our data sync. And so we have a custom code that we've written, which will read from the topic and write the data to the data sync, either in batches with some kind of time-based iterator to fetch the unprocessed records from the topic, or in a streaming fashion, where as new items are received, they are immediately forwarded to the data sync. You have choices. You can write code however you want. Additionally, because we have what is called a consumer group, the distributed messaging system will allow us to track which data is in flight if we have multiple consumers inside of our consumer group. So let's say that we had a consumer group that has two consumers, C1 and C2. And C1 and C2 are both able to consume messages and move them into our data sync. Well, when C1 is working with particular records and C2 is working with particular records, that is who has which records, and what's the state of those records is managed by the distributed messaging system. And through very standardized SDK and API endpoints that are built into this whole system. And so they are very reliable. And then if there is a crash with one of the consumers, then we can ensure that the messages that were in flight are not lost, that they remain on the topic, and maybe they're forwarded onto the second consumer, or maybe we wait to send those messages back when the consumer 1 is back online. All of these things are things that we can decide on a case-by-case basis by leveraging the features of the distributed messaging system. In addition to the scalability and resiliency that we gain within this single topic. The topic data can also be distributed across multiple multiple nodes in a cluster. So we could have replicated topic data in case one of the nodes in our cluster goes down. And in fact, some of these systems will allow you to do a full copy of the entire your entire distributed messaging system will remain synchronized between data centers. You can run two installations of your distributed messaging system with identical configuration and have one be the primary and one be the failover, and all of your topic data will stay synchronized in case that whole data center goes down if you have very, very sensitive data that you work with. So there's multiple layers to the resiliency that we can choose from that have various costs and benefits that we can use as needed for our project. The last level of scalability that's important here, I guess there are two actually we need to discuss. We can also scale our producer code independently of our consumer code. So let's say we have a data source, we're scanning records out of a, let's say an external API, and each time we make an invocation to the API, it gives us 1,000 records, and then we paginate and go to the next 1,000 records. We could easily implement a second producer, get a second API key, and then we could double that throughput by having two producers making concurrent SDK calls, or maybe we do that multi-threaded inside of our own producer code, however you want to do it, whatever makes sense. But when we scale this up, instead of the consumers immediately getting bombarded with a ton of data or having a ton of data writes into our data sinks that, maybe that would cause crashes or read failures on our data sinks, the distributed messaging system is going to store that data, and then we can continue consuming it the same way that we were before. So we can experiment with scaling up our producer without having any impact on our downstream consumers and data sinks. And this is also very, very useful for scalability and overall throughput. The last level of scalability to mention is the flexibility of the data model within the system. So let's say that we have a data source like this external API that we're calling, and we have two different data sinks that have different schemas. So let's say we have a ClickHouse database where we have particular fields that we're interested in from this API. And then we have a second data sync, like a time series database, where we're interested in only maybe a subset of those fields and not all of them. What we can do is we can configure our distributed messaging system to put this data on two separate topics. And then we can configure the second consumer to only work with the fields that are relevant for the second data sync when it does the write operation. Additionally, some of these distributed messaging systems will allow you to configure at the topic level this kind of refinement of the data, this basic kind of refinement or enrichment or transformation of the data inside of some custom tooling that's in the messaging system. So rather than writing custom codes to extract particular fields when the distributed messaging system receives the event from the producer, it will put the data in the format that you want with only the fields that you want onto this topic, and then your consumer doesn't have to deal with that part. Of course, pros and cons, not something that is available on all of these systems, but something that is out there that you should be aware of. And of course, another motivator for having this kind of pattern would be to have different types of insert operations from your consumers. So if we're writing to ClickHouse, we're probably going to want to implement batching. So we're writing large numbers of records in one insert statement at a relatively low frequency, like once a second, maybe once every 5 seconds, if we can tolerate that. And this will allow, this will alleviate write pressure on our ClickHouse database and allow our cluster to remain stable for performing read operations. Whereas in our second data sync, our time series database, it may be very optimized for streaming data, meaning writing one record at a time. And our consumer group can be configured to where as soon as there's a new data point on the topic, it writes it to the data sync, no batching or anything, just immediately as low as latency as possible. And so these are the reasons why we use decoupled data pipelines. Be sure to watch the remaining videos in this playlist to gain more perspective on architectural principles and concepts for data systems in general. And be sure to check out the playlist on distributed messaging systems. How we have a playlist for distributed messaging systems in general, just general concepts that apply to any tech, whether you're using Kafka or Pulsar or RabbitMQ or whatever. And then I also have a special series for advanced techniques and concepts in Apache Pulsar, being my favorite distributed messaging system. So with that, I will see you in another video.